Okay, today we're going to start Chapter 5, which is Work and Energy. So first we're going to talk about work. Now work is something that we do in everyday life, and we're going to see that sometimes in physics, the meaning of words in everyday life don't have the exact same meaning in physics. Okay? So work, the definition says the product, so product means multiplication, of the force and the displacement of an object in the direction of the force. Now, the equation for work is FD. F is equal to the force, and D is the displacement. We can also call it, instead of D, we can also call it X, because we've been calling displacement X all year long. So, work is measured, force is measured in newtons, displacement is measured in meters, and a newton times a meter has a new unit, and it's called a joule. Now, a joule might sound familiar from something. Has anyone ever heard of joules before? Well, maybe with some a certain part, but we know work, when we learn joules, you maybe saw that in chemistry with maybe like heat, because heat is a form of energy, and work is equal to the change in energy. So what we're going to see in this chapter is we're going to see a lot of things that are interrelated. So even though the force and displacement of both vectors, work is a scalar quantity. So scalar, remember, means that it has no direction. Okay? But will we end up with positive and negative values? And that's going to mean something. So work is done only if an object is moved in the direction of the force. So let's say I had a box, and so let's say there was something really big. Let's say I had the big lab table. So let's say my finger's like me pushing on something. So when I push it this way, if I'm pushing it horizontally, the work is done in that direction. So let's say now I push on something, and I'm pushing, and I'm pushing, and I'm pushing, and it's not moving. Is any work done? No. So a lot of times we get confused with everyday life, because when you put effort into something, if you try to move something, so let's say somebody's car broke down or someone's car was stuck in the mud, and you push and push and push that car trying to get it out of the mud, and it doesn't move. Don't you feel like you did a lot of work because you did a lot of effort trying to push it? But in physics, work is not done unless it actually moves. So if it doesn't move, you don't do any work. Okay? So here's our first example. A student pushes a desk with a horizontal force of 120 newtons and moves the desk 2 meters directly across the floor. How much work is done? So the force is 120 newtons. The displacement is 2 meters. I want to find the work. Work is equal to FD. 120 newtons times 2 meters. 120 times 2 is 240, and a newton times a meter is a joule. But again, only the part of the force that's doing work in that direction is what matters. So now this other equation says work is equal to FD cosine theta. So let's say now I'm pulling an object. So I'm pulling it with a force at a certain angle from the horizontal. So if this was on a flat surface and the object is moving this way, only the component of the force in this direction does work. So the component in this direction, remember you thought, oh, I'm done with all that sine, cosine, and tangent stuff? No, we're never going to be done with that. Okay? So if this is my force F and I want to find the components, this would be Fx, and this would be F of y. So the x, the horizontal component, is the one that's doing work. It's the one that's going horizontally. So the horizontal component, if I look at the picture, it's going to be F cosine of theta because it's adjacent to the angle. So that's why here it says F cosine theta. So only in the direction in which it's moving. But the same thing is true vertically. If I lift something vertically, the weight of the object is going to be m times g, plus that's what the force, the weight, is being moved vertically, and that would be the work. All right, here's another example. A sailor pulls a boat along a dock by a rope held at an angle of 60 degrees with the horizontal. How much work is done if the sailor exerts a force of 2.5 times 10 to the 2 newtons on the rope and pulls the boat 30 meters. So I'm going to write my given, theta 60 degrees. I'm going to write the force, and I'm going to write the displacement, and I want to find the work. So W is equal to FD cosine theta. A Newton times a meter is a joule. When I use my calculator, I'm going to, again, be careful with the sign. I'm going to make sure my calculator is not on radians. And so I would go 60 cosine times 30 times 2.5 EE2. So it says 3750. And then if I want to put in correct scientific notation, second there, and 3.75 times 10 to the 3. Okay? Now, in this class, we can also look at things graphically. So the graph we're going to look at is a force versus displacement graph. So on a force versus displacement graph, the area under the curve is equal to the work done. So you might either draw a graph or they might show you a graph. Now, the problem here is this part's curvy. How do I find the area under the curve when it's curvy like this? And remember, when we say the area under the curve, we're not just talking about the area that's curved, we talk about this whole thing. Well, if it's curvy like this, I'd have to use calculus. But a lot of us maybe are not in calculus yet, so if they ask us this, we can easily find the area of this. This is a rectangle, and we could do base times height to find this rectangle. So when we end up having a test, and on standardized tests, the most common question is I'll have a graph, and it'll be an easy graph with shapes like rectangles and triangles, and I'll say from like 0 to 1 second how much work is done. And if it was a triangle, you do 1/2 base times height. Okay? So here's an example here. It says a constant force of 50 newtons is applied over a distance of 10 meters. A, prepare a graph of force versus displacement. B, calculate, this should be area, the area underneath the curve, and then calculate the work done. So here's the graph. B, the area is going to be, this is a rectangle, so it's just going to be base times height. So this is 10 meters times 50 newtons. 50 times 10 is 500, and newton times a meter is a joule. And then they say, what's the work done? Well, the work done is the area under the curve, so I didn't have to actually calculate that. And then the last thing for today is going to be talking about energy. Now, in middle school, you learned about energy. You learned about potential energy. You learned about kinetic energy. The difference, bless you, between middle school and high school is obviously in physics, we're going to do more calculations. And even when we do conservation of energy, we're going to see how energy is transformed from one type to another. So energy is the ability to cause changes in matter. Energy comes in many forms. This is not the only chapter we're going to be talking about energy or types of energy. Without energy, work cannot be accomplished, and energy is present in all matter and can be changed from one form to another, but cannot be destroyed. So the first type of energy we're going to talk about is kinetic energy. So when you think about kinetic energy in layman's terms, kinetic energy is the energy of motion. It has to do with things moving. And when you look at the equation with kinetic energy, it has V in it for velocity. So the word kinetic itself means moving. So kinetic energy is 1/2 mv squared. So it's 1/2 the mass times the velocity squared. So again, in order for it to have kinetic energy, something has to be moving. So energy is measured in terms of the work it does or can do. So energy has the same units as work. Like work, energy is a scalar quantity. That means it doesn't have a direction. So let's look at some examples of kinetic energy. So a coiled spring unwinds. Dynamite explodes. Batteries used to make a toy run. Water behind the dam is released and a rock topples off a cliff. And the reason I gave you these examples is when we start talking about potential energy, and I give you an example, we're going to look at the same types of things, but how they relate to potential energy. tomorrow we're going to do the work energy theorem. But today, all we need to know for our homework is kinetic energy. Oh no, we're going to do that also today. So let's go over this. So the work energy theorem basically says work is equal to the change in energy. Well, delta means the change, which is the final minus the initial. So this says work is equal to the change in kinetic energy, the final minus the initial. So let's look at our example. It says an 8 kilogram mass, so we're going to write our mass as 8 kilograms, moves at 30 meters per second. A, what is its kinetic energy? If the object was initially at rest, so the initial velocity is 0, how much work was done on the object to give it this kinetic energy? So for the first part, kinetic energy is 1/2 mv squared. So 1/2 the mass times the velocity squared. Now let's look at our units to make sure they work out. So we have a kilogram. When I square the 30, I also have to square the units. So this is going to be meters squared per second squared. Well, if I pull out everything except one of these meters, I can have a kilogram meter per second squared times a meter. So this is a Newton times a meter, which is a joule, which is the correct unit for energy. Part B says how much work was done. So work is equal to the change in kinetic energy. So the final kinetic energy, which I already solved in Part A, minus the initial, which is 0. Because if I plugged it in, KEI is 1/2 MVI squared. Remember, VI is 0. So anything times 0 is 0. And again, we're just introducing. This is the beginning part of the chapter. And then as time goes on, we're going to learn potential energy and then conservation of energy. And that's it.